Thank you very much for the invitation. Today I'll be talking about noise protection. Is it essential or an unnecessary luxury? First I'll tell you about the outline. So why is noise protection important? Secondly, I'll talk about how noise protection is regulated in Germany. Then we'll discuss how sound travels in buildings, and knowing that, we can explain how sound insulation can be increased. And finally, I'll end with an example of best practice applied to stairs. So why is sound insulation important? Well, the main cause or reason is health. When people hear noise, they get in a flight situation, so your body wants to run away. It lets out stress hormones like adrenaline, which makes your heart pump faster and your blood pressure increased. If this happens to you very often, you can get chronic heart disease and even heart attacks. The WHO, the World Health Organization, says that there are 100,000 people who die from noise pollution every year. And there are about 1.6 million healthy life years that are lost every year in Europe. Secondly, comfort is important. You can imagine if you're sitting down wanting to read something and your neighbors are making a lot of noise or there's loud noise from outdoors disturbing you, then it's uncomfortable. That's one main reason. The final reason, which my dog Chica was nice enough to help show, was sustainability. If you build a house and it has poor sound insulation, nobody will want to live there. So either it'll be empty or it would have to be retrofitted, which costs a lot of resources, time, and energy. Now, how is it protected and regulated in Germany? Well, it's done judicially. There's a standard called the DIN 4109, or DIN 4109, that talks about noise protection in building construction. It has three main parts. In the first part, it talks about the regulations. So, how good does the sound insulation have to be from outdoor noise or from indoor noise from your neighbors, for example? It also talks about for different housing types. So, if you have a hospital or if you have a multi-family dwelling or row houses, they have different requirements. And also, for different room types, like sleeping rooms or bedrooms or hallways or toilets and bathrooms, they all have different minimum requirements. So those are all defined in part 1. Part 2 now tells you how to calculate the sound insulation or the levels in the rooms. That's the way to get these requirements proven. So you don't have to go measure in the field, but you can calculate them in advance. And to be able to do so, use all these formulas in part 2, you can use part 3, that is a summary of all these databases with all the properties of different types of construction. So now we know how to regulate it, but how does the sound travel? Well, before we can do that, or talk about that, we have to know what kind of sound sources there are. So you can see a few, and you can even hear me. I'm speaking. You could be laughing or singing, la, like this. At this point, I'd like to thank my daughter for the nice drawing she made. When I'm singing, it moves the particles back and forth. Then they excite the next air particles, and the sound travels through the room. It can hit against the wall, make the wall vibrate, and those vibrations of the wall radiate sound into the next room, and that's the noise you hear by your neighbors. Those kind of sources are called airborne sources. You also, of course, have impact sources, with different types of shoes, soft ones or hard ones. I forgot my high heels today. Or it could be pulling a chair, or kids jumping up and down, or playing with their Legos. All of those are types of impact sources where you can impact the floors or the walls and the sound gets transmitted like that. So we know which kind of sources there are, but how does the sound travel? Well, first you can see it for room pairs. If you have pairs of rooms, one above the other, as this case, you talk about vertical transmission. And the first path is usually the direct path. So in this case, it goes directly through the separating floor, as you can see. Then there are also paths that are called flanking paths, and they go around the separating element. So they go, for example, into the wall and out of the other wall, or they go into the floor and out the wall, or a path I didn't show would go into the wall and out of the floor. So at each of those wall-floor junctions, and there are 4 of them in a square room, you have 3 of these flanking paths, which makes a total of 12 flanking paths and 1 direct path. If you have these rooms above the other, if you turn it on its side, you don't talk about vertical transmission anymore, but you talk about horizontal transmission. And here now, the separating element is not the floor, but the wall. So the direct transmission is through the wall, and the flanking paths go all around it. You also have diagonal transmission. So the sound can go into the floor, around the junction, and into the diagonal room. This is also very important for stairs or for balconies where you have these flanking paths. So now we know which type of sources there are and how they travel. So now we want to know how we can stop the sound from traveling, or how we can increase the sound insulation. One easy way to do it is to add mass. For example, if you have a wall 10 centimeters thick and you want to increase the sound insulation, you can double it. You double it, the thickness, to 20 centimeters, and then you have an improvement of 6 dB. If you double it again, then from 20 to 40 centimeters, you get another 6 dB improvement. Well, to help you understand what this 6 dB means, a person perceives an increase in sound of 10 dB to a doubling of the level. And if you decrease it by 10 dB, it sounds half as loud. So making a wall 4 times as loud is similar to making the sound in the receiving room half as loud. This only goes so far. If you'd want to add another 6 dB, you'd have to turn your 40 centimeter wall into an 80 centimeter wall, and that sounds ridiculous. So there's a much more elegant way to do this, and it's by decoupling. So if you have your floor here, for example, you can use this technique in many ways. You can add a floating topping on it. That's another mass and an interlayer that's soft. And then if you excite that floor, or that floating topping, not all the sound will get transmitted to the bottom. You use this technique for hung ceilings, for wall linings, for stairs, for landings, or for balconies. I'll explain it in this next slide. Here you can see there's the frequency on the y-axis, the frequency on the x-axis, and your improvement on the y-axis. At low frequencies, adding this interlayer, this soft layer, has no improvement. At the resonance frequency, it actually makes a worsening depending on how much damping is in this layer. And at high frequencies, you decouple the system and you don't get that much energy transmitted from the one element to the other. I can show this a little better with some videos. In the low frequencies now, if you excite the one element, the other element moves just the same, and the vibrations are just the same as on the other element, so it transmits sound and radiates as much sound. At the resonant frequency, you don't have to excite the one element that much, but still, the vibration of the bottom element is much higher, and it radiates more sound, so a little worsening. The area where we're concentrating on is above this resonance, where you can excite the one element with your feet, for example, and the lower element doesn't move at all. So that means there's no vibration, then there's no radiated sound. And that's how you can elegantly improve the sound insulation of a system. I'll show you some examples of this for stairways. So here on the left, you're decoupling the landing by using some interlayer, and it's a soft type of layer, and you have to make sure it's not too soft, but otherwise they'll be touching each other and you have the rigid connection again. But you can also set these in between the stairs and the landings. So this works very good, and I'll show you some examples of some measurements. So now on the top, you have a landing connected to a wall, and it's excited by what's called the ISO tapping machine. This is a standardized source that has 5 hammers that hit on the floor, and at a certain rhythm and a certain height and a certain speed, and it's standardized. And that excites the landing, which excites the wall, which then radiates into the room. Now you can also decouple the landing, and you can see there that it also excites the wall, but just much less. If you want to look at the normalized impact sound level, that's the level that you measure in the side room, you can see them here. The blue one is for the coupled landing, and the red one is for the decoupled landing. And you can see at the low frequencies, there's similar values, and in the mid frequencies, you start getting an improvement, and at the high frequencies, you see much, much better results. The levels are about 40 dB quieter. You can do the same thing for stairways as well and decouple them from the landing. So again, the top, you first connect your stairs to the landing rigidly, and then you can decouple them from the landing with this interlayer, and then you can measure this, and you can see again at the high frequencies above this resonance frequency, you get very good results. So this resonance frequency, it's important to shift it very low, and you can do that by making these layers very soft. Again, you can't make them too soft, otherwise they will just be squished and connected again. Here you can see how it's done in practice. you can see all the decoupling done from the walls, from the landings, and from the stairways on the left. In the middle, you can see one of these elements, these landings, where you already have all the layers attached to it, and it's put into the stairway. And on the right, you see the expansion diagram where you can see all the decoupling happening everywhere. Well, now we can come back to the initial question, noise protection, essential or unnecessary luxury. I think we'll all come to the conclusion that it is essential and that solutions exist. Thank you very much for your attention.